Okay. So today I'm going to be drilling down more on algorithms because even though I've been in the engineering field for a while and I used to know a lot more about this, there seemed to be like a lack or rustiness in my part of working through these particular coding issues. And it's something that when you're in the real job, it's you rarely run into problems that actually need such a targeted response. So today I'm going to be working through the coding different coding interview patterns and working down through some of these algorithms just to get a better idea of intuition on improving efficiency, and side note to improve my own Python coding skills. So that's what we'll be coding in for this particular things, but this is the actual understanding of how these systems work um, transcends the the language itself. So we're going to start with 2 pointers today. What we're going to do is we're going to understand the strategy in and of itself, and then we're going to apply it to a few coding questions. And later on, in further streams, what we will do is we'll work through other sections of ByteByteGo and other various platforms coding interview pattern or strategies, basically. So, without further ado, let us begin with Introduction to 2 pointers. Now, I will go ahead and read this out loud so y'all can follow along. But as the name implies, a 2 pointer pattern refers to an algorithm that utilizes 2 pointers. But what is a pointer? It's a variable that represents an index or position within a data structure like an array or linked list. Many algorithms just use a single pointer to obtain or keep track of a single element. Introducing a second, first let's take a look at this image. So as we hear here, I is indicating that it is pointing to somewhere within this list of numbers, that I is pointing at this particular element. Now, introducing a second point opens a new world of possibilities. More importantly, we can now make comparisons. With pointers at two different positions, we can compare the elements at those positions and make decisions based on the comparison. So, compare element at positional index I to element at positional index of j. In many cases, such comparisons are made using two nested for loops, which takes O of n squared time, where n denotes the length of the data structure. In the code snippet below, I and j are 2 pointers used to compare every two elements of an array. Now, let's take a second and think about this. So O of n to the second power, meaning that it is exponential growth. That means for every single iteration, or for every single loop, for every single item in the first array, you will perform another loop of the entire length of the array for each one that you go through. So what does that look like? Well, let's go ahead and get an idea of what that looks like. So if we were to do two for loops, and to just show that out, it would look something like this. So let's go ahead and create an array of 5 items, and so we'll do list. We'll actually just call this array equals 1, 2, 3, 4, and 5. And then we'll go ahead and loop through these and print them out twice. So for item, for num, and array. Oh, it was also help if I was actually writing this in a code block. Terminate, we'll go ahead and print num. And then we will go ahead and say for num2 in array, shall print do an f string, and we'll say num equals, and num2 equals. Go ahead and get rid of this other one. We'll go ahead and let that run. First time running this, so it's going to take a little bit of things. But as you can see here, we'll see that for each iteration, so we see that there's 5 ones here. And then for each of the ones, we have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. And then we start with the second one of 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. Now this is, in effect, O of n to the squared. So this is what they were referring to. Now, same thing here. They just do it with a range. Is for I in range of n, for j in range of n, compare these two numbers. Often this approach does not take advantage of the predictable dynamics that might exist in a data structure. An example of a data structure with predictable dynamics is a sorted array. When we move a pointer in a sorted array, we can predict whether the value being moved to is greater or smaller. For example, moving a pointer to the right in an ascending array guarantees that we're moving to a value greater than or equal to the current one. Now this is where inside of your problems, when you're looking at a particular LeetCode problem, and let's go ahead and take a look at two sums here. You can see that in the input in a lot of these, the array is not necessarily, let's look at example 2. The array is not necessarily sorted. So there is a element that when you're tackling these kinds of problems that you will need to bring some semblance of order to the data structure that you are working with. So, as we continue, as you can see, data structures with predictable dynamics let us move the pointers in a logical way. Taking advantage of this predictability can lead to improved time and space complexity, which we will illustrate with a real interview problems in this chapter. So, now that we do that, let's take a look at the various strategies that can be utilized in this particular, the sub strategies that can be utilized in this particular, for this overall topic. So 2-pointer algorithms usually take only O of n time. Let me restrict that. 2-pointer algorithms usually take only O of n time, or linear time, by eliminating the need for nested for loops. There are 3 main strategies for using 2-pointers. The first of which is inward traversal. This approach has pointers starting at opposite ends of the data structure and moving inwards towards each other. The pointers move toward the center, adjusting their positions based on comparisons until a certain condition is met, or they meet/cross each other. This is ideal for problems where we need to compare elements from different ends of a data structure. So what would this look like if we were to have this? Let's break this down into its components here. So we have 2 pointers and they're moving in between the array until we meet or cross each other. So let's build out a simple example of this. So we'll go ahead and create this. So we'll do sub strategy, and it is called inward traversal. Okay, so like we said in before, it is the aspect of 2 pointers moving closer together. So let us create a new list. So we're going to have an array equals to, and let's do the way that they had it in before, so range, and we'll go to 10. Let's make sure that this array is what we expect it to be. Oh no. Let's pack this up. This is where actually I think I could just do I for I in range 10. Help if I spelled it correctly. Yep, there we go. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So that gives us our list. So now we're going to instantiate those 2 pointers. We're going to have our left pointer, which is going to be equal to 0. And then we're going to have our right pointer, which is going to be equal to and let's actually make this a little bit more clear, because I want to make it, my personal preference is when I'm working with variable names, I want to have a very clear distinction, like if I come back to this in 2 months, that I know exactly what I'm looking at. It's not just an arbitrary name. We're not arbitrary. It's not a leading name to understand it. Now, other people might disagree with this. It definitely takes up space. It's probably not the best thing in general. However, for learning purposes, well, in general, depending on what you're working with and depending on language, it might not be that bad of a problem. But for this point, we're going to make them very explicit. So we're going to say left pointer, and it's going to be equal to 0. And then we're going to have our right. And apologies for those who are Arabic. I know that it's backwards. I don't know. You know what? Thanks. Anyways, we'll have array, the length of array -1. So this will give our 2 pointers. So let's go ahead and print those out. So we have printer. We're going to do an F string again, and we're going to do left pointer. We're going to do right pointer. Right, and then we'll go ahead and things. So we now see that we have our left pointer pointing at index 0 and our right pointer pointing at index 9. Now, what we shall do is that while our left pointer is less than our right pointer, we are going to move them. So let's see, how should we do this? How does the picture work? So they have them both moving at the same time. So let us do that similar strategy. So we'll have left pointer is plus equals left pointer plus 1. We'll have right pointer equal to right pointer -1. And then what we're going to do is we're going to print those. So we're going to come up here, print these, and then we're going to go ahead and run that. Okay, so now, as we can see, we can move them. We're moving them closer and closer and closer together. So 0 and 9, 1 and 8, 2 and 7, 3 and 6, 4 and 5, until they meet the left pointers at 5 and the right pointer is at 4, and they've crossed. So this would be a very rudimentary inward traversal. So let's go back to and take a look at what the second strategy is. So the second strategy is unidirectional traversal. In this approach, both pointers start at the same end of the data structure, usually the beginning, and move in the same direction. These pointers generally serve 2 different but supplementary purposes. A common application of this is when we want one pointer to find information, usually the right pointer, and the other another to keep track of the information, usually the left pointer. Okay, so let's talk about that. Alrighty, so moving on, so we have our second strategy here, so sub-strategy, which is called the unidirectional traversal. Unidirectional traversal. So, and let's also start coming up with, because one of the goals with this is to remember it, right? These are only so good as if you remember, oh yes, this is how this particular algorithm works, and this is the strategy, and this is how I can conceptualize it. So if we break these things down, so inward traversal, if we say inward, we can understand that inward stands for where we can infer from inward that we have started on the outsides and making our way in. So inward, start on the outside and make our way towards the and make our way toward inward, way inside. Start on the, there we go, yeah, inward. So start on the outside and make our way to the inside and proceed inside. Let's make this even more concise. Proceed inside. All right, and traversal is, I think traversal, we can imply this, there's an implication here that we go through the entire data structure. So that's where we start on the furthest minima and maxima of the data structure. So if we were to say that, traversal, let's see, the process of which the inner travel traverses or spans the entire structure. Good. All right, so just a way to kind of keep that in mind. I know that I'm personally trying to keep this all in there with everything else that you got to remember, but at least we come up with a better way to emphasize this, because learning, a part of learning is coming up with ways that you personally can internalize and understand the concepts or the thing that you're trying to retain. So an element of this is rewriting in your own words, coming up with your own understanding of how something works. It's that extra 20%, that extra effort of not just reading, consuming, and doing, but truly understanding what you're working with. Alrighty, and let us now move on to unidirectional traversal. So, as we did before, it's the moving of left to right. So, let's break this down into its, I'm going to find this real quick. I think that's it. Nope. We will just do the old-fashioned second break. Alrighty. Now, unidirectional. If we were to take this into consideration, let's talk about this. So we have uni, which means one. Super fancy. Directional, direction, which is the way you go. The way we go. Direction, I'm just a little, you know what, direction is pretty self-explanatory. We're just going to leave it at direction. Then, traversal, we are going, we're going to do the same thing of spans the entire structure. So, what is the way we do this? We can say, well, this is the how is a good way? The traversal, the journey, the one-way journey through a data structure. Yeah, that seems good. Now, what was one of the things? Now, one of the things that they said in there, that's the key thing of like, why do we use this particular strategy? Of all the other ones, why are we using this particular strategy, sub-strategy? And the way that ByteByteGo said it is the first pointer keeps track of information, and the second searches for the second. Searches for an additional piece of information. Excellent. So let's take a look at this and let's write a simple example here. So let's go ahead and get our range, and I'm going to do something slightly different with this one. We're going to start with, so we're going to start on 1 and we're going to make our way to 10. So I want that to be 11. Let's go ahead and check this to make sure I'm right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. All right, let us create our pointers. So, and key thing in here, just to make sure that we're all on the same page, is that this is a Jupyter Notebook. And what does that mean? Is that Jupyter Notebooks keep state for that session. And what does that mean? So if I was to say left pointer here and not make any changes, and we were to just go ahead, it would say 5. But 5 is where it was last time. So we got to make sure that we reinstantiate all of these things in between each of these sections. Obviously, we could use a regular Python file, but for this purposes, I like the documentation and journey, the self-documenting and journey process that Jupyter Notebooks allow in a research-ish kind of way. Note taking. So just something to keep aware of. So what we're going to do is we're going to reinstantiate the left and right pointer each time. Now, luckily, since we're reusing the names, what we can do is we can select this. We can set it here. And then one of the things about this, so the first pointer in the second search, and since we're only ever going in one direction, this should also start at 0. So our left and right pointers are now both starting at 0. So let's go ahead and we shall show this. Oops. Oh, boom. All right, and we'll run that. Here we go. Left and right pointers are both pointing at 0. So let's create a situation where for each number, we want to print a combination of the two. So let's see. How can we make this? Okay. Here's a way. So we're going to make this slightly interesting. Let us think about two dice. Two 6-sided dice. We're actually might need to move this around, but we're going to make a slight problem statement here. Actually, you know what? We're not going to do that. The reason why is we're going to just stick with the basics, stick with the components. Let's not make this more complicated because we got toy problems to get to, and those ones will probably have much better examples than something I can come up with. Most likely I can probably come up with something and it might be more fun, more intriguing, especially if you're a board gamer. But for this thing, we're just going to stick with, let's just show it as we is. So we want to find a combination where our numbers add up to a particular thing. So we're going to find our case. Our case is going to be, let's find two numbers that equal 15. We're going to find the first two numbers that come out to 15. So while left pointer, let's do this. While array left pointer plus array right pointer does not equal case. Okay, I don't know if this will work, but we're going to go ahead and test this. Let us see. So, beginning with this, let's go ahead. We are both of our pointers and right pointers. So, we are going to do a left pointer let's say if our right pointer is less than the length of the array, we are going to right pointer equals right pointer plus 1. Else, we are going to say right pointer is equal to right pointer is equal to, let's actually not quite that, let's say left pointer is equal to left pointer plus 1, and then we're going to have right pointer is equal to left pointer because we want them to come back to the same place. We've moved on and now we're saying, okay, nope, that's not quite what we want to do, let's move back. This again, we're not sure if this is the exact same way, but ideally this is implementing, we are both going in one direction, and we're looking for a case, and we're using the left point to say this is the number we're looking for, and the right pointer to search out another condition which makes the case true. So let us do this, and for the sake of fun, we're going to go ahead and add our print statement here once more. And then at the end, we're going to have a print statement that says f square, our case is equal to number array, bracket left pointer, plus brackets array right pointer. And if you do have the question here of like, why are you doing this? This doesn't really make any sense. All right, list index at a range. We need to do here we go. Okay. Yep. So there we go. 15 is equal to 5 and 10. That's the first combination of two numbers in our array that equals 15. So now that we understand that, let us move on to the next bit. And we could probably do this in a way that, let's make this simple. That's the thing. We now have a way where we are going from left to right, looking for a pair of information that meets our case. So let's move on to substrategy numeral 3, stage traversal. In this approach, we traverse with one pointer, and when it lands on an element that meets a certain condition, we traverse with the second pointer. Similar to unidirectional traversal, both pointers serve different purposes. Here, the first pointer is used to search for something, and once found, a second pointer finds an additional piece of information concerning the value at the first pointer. We discuss all of these techniques in detail throughout the problems in this chapter. Good, so we'll come back to this, but let us think about this. So in this image, so what we're saying is that we're moving through with one pointers until we find that particular case. Then the second pointer can go in any direction, but it initializes at the point of where the first pointer exists. And it goes along its merry way. So let's see if we can put this up. So first off, let's go ahead and put this into the notes. Okay, staged traversal. Substrategy. Staged traversal. Now, staged traversal, let's go ahead and break this up. Staged. Well, staged implies that there are multiple parts to it. So a multi-step, let's say solution isn't the right thing, a multi-step process, because it's not necessarily a solution, because I'm assuming that when we get into more difficult questions that any of these particular strategies or sub-strategies could be combined together to create an overall strategy or an overall solution for a given problem. So, with that in mind, let's go ahead and break this down further. So it's staged process. So, stage, a multi-step process. Traversal. I think that we've come up with a pretty good name or understanding of it from the last one, which is we're gonna split this up. The spanning or the movement. I actually like movement instead of spans, as we're coming upon this iterative piece of this. Let's change that to movement through a data structure. Okay, so we have a multi-step process. Let's go ahead and break that down. So I think we did a little bit, and I know I say we should break that down. That's a thing. Let's break this down further. I'm new with this. Give me a break. Alrighty. Stage traversal. So a multi-step process. Step 1. The first step in our process is to use our initial or our first pointer to find a given condition. Then the second step, or step 2, the second, actually, you know what, let's even things. Let's make this even more clear. 1, use the first pointer to find a given condition. 2, when the condition is met, initialize pointer to our second pointer. So we'll call it second pointer. The second pointer. And there's where we come in, 2 pointers. Okay. When the condition is met, initialize the second pointer. Then, using the second pointer, traverse or move through the data structure to locate an additional piece of information. So, to find a given condition, slash, and keep track of it. Or we can even do and point to it. Then the best thing about this is what if, say, we are looking for a second condition to locate an additional piece of information to meet a second condition. So what this is saying is that this is a multi-step process. Not only in just the fact that we use the first pointer to move through our data structure till we find a given piece of information, and then using the second pointer to attempt to try and find another piece of information that makes sense to our second condition, but it is not limited to the fact that we just once the second pointer goes on its merry way, it will come back with the correct solution. What this means is that we could even do this process again. Say the second pointer continues to go in either direction down the data structure, but it doesn't find that second condition that we are looking for. Instead, it comes up empty. Well, then we can continue the first pointer on until we find that second piece of information. So it might be a multitude given problem, multiple step problem. So let's go ahead and try and come up with a very naive example of the stage traversal. So let us create our things. So I'm going to go ahead and grab our specifics here. The array, left pointer, right pointer, and then we're going to move that down here. Alrighty. So we have an array of numbers 1 to 10. We have a left pointer 0 and our right pointer we don't want to initialize yet, so let's go ahead and say none. Okay, maybe not any of the best things, but let's go ahead and take a look. Looking good. Okay, so what do we want our case to be? So our case to be something super naive. Let's see, I'm thinking of negative numbers. So negative something negative, so that I have to find the first number and then go back down. Okay, what we're going to do is we're going to find our case is that we want to find two numbers that add up to -3. So case is equal to -3 while left pointer, actually, you know what? we can just go up here, copy our case. While left pointer minus right pointer does not equal the case. Okay. So, first thing we want to do is we want to say if array brackets left pointer is less than the absolute of case left pointer equals left pointer plus left pointer plus 1. I'm missing a ton of edge cases here for sure. Let's see, because my goal is -3, so it's going to end up on 4, -1. You know what? I'm not going to worry about it. We'll get to press questions later. Stick with the thing. All right, so if my left pointer is less than the absolute value of the case, absolute meaning that it does not matter what sign it is, it will be 3. And we can double check this real quick if we wanted to. Let's do that. Let's go ahead and open up another thing. We'll say, is -3 equal to the absolute value of -3? And this is where coding is kind of cool, because you can just things. All right, I need to use the double equals false. Why? Oh, duh. Because absolute 3 is, yeah. That makes complete sense. Yeah, there we go. 3 is equal to the absolute thing of 3. Okay, moving on. So once we've met this case, we are going to then, this is going to be a one-step example because, again, simplicity's sake. If things, else if else, we're going to say right pointer. So we need to think, so we're going to initialize right pointer. So we'll go ahead and say right pointer is equal to left pointer. And then we're going to say right pointer is equal to right pointer minus 1. And then we are going to do our age-old printer. Apparently I didn't spell that right. Grab this. Right. Alrighty, where list of indices must be integers or slices. It doesn't like it, so we're gonna go ahead and do it at the same point. Okay. Am I gonna shoot myself in the foot with this? I'm probably gonna shoot myself in the foot with this. I know I'm gonna shoot this. I know that I'm gonna shoot myself in the foot with this. Okay, so what is a better way of initializing this? Okay, you know what? We're gonna start with right. We're gonna start at pointer index number 1, because if I had left them both at 0, they would actually end up breaking case before right pointer actually did anything. So, so we're going to do this. And then we're going to actually grab our case. Here, and then we're going to go ahead and run this. There we go. Except for the fact that this needs to be minus, because copy pasta. All right, there we go. So 3 minus 6. 3 minus 6. Negative 3. Hold on, that's not quite correct. Ah. And right pointer does not equal left pointer. Ah, this is getting messy. I don't like it when this is getting messy. Okay. Anyways. That's not correct either. Okay. In my understanding, it should be 4 minus 1. Ah. That's not correct. 4 minus 1 is equal to 3. But not negative 3. To get that, it would actually be 6 minus 3. That is correct. So, let's go back here and think about our first case here. So 2 times our absolute case. So we see this here. They both start at 0. Left pointer and right pointer go to negative 1. Oh, this is because I need to initialize these separately. Or you know what? I'm just going to change my case true if if right pointer does not equal none and left and right pointer equal case. Okay, there we go. Excellent. Now we're seeing it go through. They're both do. All right, we get to left pointer is at 5. And then which isn't quite correct. There we go. Whoa, that's a wonky way of doing it. I needed to set up an edge condition here. So what happened was the left pointer went to 6, right pointer circled back around to 10. And at that point in time, it is actually 7 minus 10 is -3, which is not the answer I was looking for, but it's actually really funny. Good to see that. This is left. I wanted to get to 6 and do 3. So so we did this. Where are we going wrong? The array left pointer is less than 2 times the case, which is 3, which is 6, while the number no, that should be thing. So we get the 6. Let's just make this straight up. Oh. And I don't want it to go up, so and right pointer is equal to none, but we're gonna have to do something here is that's no bueno. Okay, getting this case thing is actually a lot more difficult than we think it is, because I can't just immediately do this, otherwise I'd make let's say less than. So we have array or left pointer is less than 6. Because it needs to stop. I don't want that left pointer to move anymore. At that point in time, then I'm looking for my next case. If and this is, again, very, very naive example. So what I'm saying is, if the array is not, if we didn't find our second case, our starting case, then continue. Not equal our case. And then we're going to have our break. Okay, let's this. go. Oh, shoot. I am getting very tired, as I should have seen that. Once we meet that case, I need the right pointer to be initialized. Oh. There we go. Duh. Hey-ya! Okay, that took us way longer than I wanted to, but you know what? We'll cut it down in post. Not actually. Because I don't do post. Not yet. Alrighty, so I just had my case. So what is instead of thinking this as a failure, all failures are just a lesson in disguise. So therefore, if we were to think about this as a lesson, what was the lesson? The lesson of that we have learned here is pay attention to your cases. So the lesson to take away is that the cases used in this I think it's going to be anything. The lesson to take away is when making a case, ensure that you understand how or what values or pieces of information lead to the case. Now, what does that mean? That means looking at the values involved in the case. That means looking at the positional nature of the values in the case. So, and in what circumstances, or when does the case, or I want to say limit. Here we go. Limits of the values, limits to find the values to solve the case, which is a fancy way of saying constraints. All right. So we've taken that failure and turned it into something more, a lesson. Now. Let us go back to our thing, so which is when to use 2 pointers. So we've learned the strategies. Our strategies being, and let's see if we can remember this, inward traversal, unidirectional traversal, or one-way traversal, inward traversal, one-way traversal, and multi-step traversal, or multi-stage or stage traversal. Yeah, stage traversal. So multi-step traversal. Okay. When to use this? So a two-pointer algorithm usually requires a linear data structure, such as an array or linked list. I think that there's other ways that you could probably do that, but we'll figure those things. Otherwise, an indication that a problem can be solved using the two-pointer algorithm is when the input follows a predictable dynamic, such as a sorted array. Predictable dynamics can take many forms. Take, for instance, a palindrome string. Its symmetrical pattern allows us to logically move two pointers towards the center. As you work through the problem in this chapter, you'll learn to recognize these predictable dynamics more easily. Another potential indicator that a problem can be solved using two pointers is if the problem asks for a pair of values, or a result that can be generated from two values. So when you're in an interview and you're thinking, okay, I need to solve this problem, if there are keywords and those keywords are saying pairs of values generated from two values, those keys, those clues should point you towards using a two-pointer strategy. So let's go ahead and we'll move this up to the top, and we'll go ahead and let us put that in there. So when to use. Finding a pair of values in a predictable linear data structure, or finding the result of two values in a predictable linear data structure. And with that, we are now, and let's double check our understanding there, pair of values or a result that can be generated. So let us go into a real world example here, which is great. I actually really like the fact that they are putting it into a thing to think about. This is what it's used. How does this work in a real world situation? So their example is a garbage collection algorithm. In memory compaction, which is a key part of garbage collection, the goal is to free up contiguous memory space by eliminating gaps left by deallocated, or aka dead, objects. A two-pointer technique helps achieve this efficiently via a scan. A scan pointer traverses the heap to identify live objects, while a free pointer keeps track of the next available space to where live objects should be relocated. As the scan pointer moves, it skips over dead objects, shifts the live objects to the position indicated by the free pointer, compacting the memory by grouping all live objects together and freeing up continuous blocks of memory. So what does that look like? That means if moving through, you keep track of the last live one, keep moving. When you find a dead object, you would move the live object to where the dead object is, and then, yeah. So you're just doing a bunch of switching? So live, dead, live. Dead gets switched with the live. No. Live, dead, switch. Switch. Okay, so you last known live, moving the second pointer till you find the next dead, swapping it, starting over from where the dead is, now, moving forward until you find the next dead one, switching the live and the dead, and then just moving through all the way through. And you know what? There's another part of that is if you already know that all the previous elements before it are in fact alive, you could start from the last known position of that dead argument and continue to move through. Therefore, you're not repeating movements over known live entities. Okay? Yeah? Alrighty, so chapter outline, we have 2 pointers, and it has 3 strategies, which is inward traversal, pair, sum, sorted, triplicate, sum, largest. Oh, they're just naming. They're naming particular problems that fall under particular strategies. Okay, so with that in mind, we're going to go ahead and move here. Now, I'm actually going to stop here and then come back to this another time, mainly because now that we've covered the 3 strategies that are involved, we can come back and start to actually solve these. But this isn't my first job. I have lots of other things that I need to do, and 1 hour is plenty of time. So I will bid you all adieu. Thank you for joining me if you were here. If not, then I will be uploading this to the LoopTubes, and we'll see how that goes. So, au revoir.